Watch the cat in this video. Now watch what happens when an AI removes the cat. The Jenga tower stays standing. The blocks never fall because the thing that pushed them never existed. Same trick on a bear holding a balloon. Take the bear out, the balloon floats up like it always should have. Take a hand off a spinning top and the top keeps spinning, untouched, as if nobody was ever there. This is Void, an AI from Netflix research. It deletes things from video and rewrites everything those things caused. Today we'll look at how it does that and the strange reason it works at all. Every other AI video tool fails this. They delete the pixels behind the object, then leave everything else exactly the same. The pins still fall over, the blocks still tip, the vase still breaks. The hand isn't there anymore, but somehow its consequences still happen. Deleting something from a video shouldn't just hide it. It should rewrite every single thing that thing caused, and until now, almost no model could do that. The obvious idea is to use a physics simulator. Drop everything into a 3D engine, delete the object, and let physics replay the scene. Easy. Except a video doesn't give you a 3D scene, it gives you pixels. To run a simulator, you'd need full 3D models of every object, plus their masses, frictions, joint constraints, the lighting, the camera path, the textures. None of that is in your phone clip. Recovering it is 5 different unsolved problems stacked on top of each other. And even if you somehow reconstructed all of it perfectly, the re-render wouldn't look like your video anymore. It'd look like a 3D animation. Sensor noise, motion blur, lens distortion, all gone. You'd spot it right away. So a real simulator is out, but maybe a fake one isn't. Here's the trick. You can't run a simulator on real footage, but you can absolutely run a simulator to make training data. So that's what they did. They used 2 of them. Kubric, an open source simulation and rendering pipeline that drops random objects and simulates collisions. And HUMOTO, a 4D motion capture dataset of humans interacting with objects. For each scene, they ran the simulation twice. Once with the object, once without. Same starting state, same lighting, same camera. The only difference was what happened next. Think of it as running the universe twice. Roll back to the same starting moment, delete one thing, press play. You get a perfect before and after pair, the kind that physics in real life would never let you film. Strangest part, Void is trained almost entirely on these synthetic clips, cartoon blocks, gray mannequins. Yet it works on real bears and balloons and spinning tops. Here's the reason. Void doesn't start from scratch. It's a stack of 3 models, each one fine-tuned on top of the last. At the bottom, CogVideoX, trained on millions of real internet videos. That's where it gets its sense of what real footage looks like. On top of that, a model called Generative Omnimatte that already knew how to do layered video editing with mass conditioning. And on top of that, Void itself, fine-tuned on the Kubric and HUMOTO pairs. The synthetic pairs only have to teach one narrow new skill. What should physically happen when you remove something? So how does the actual editing work? You give it a video, you click on the thing you want to remove. First, a tool called SAM2 takes your click and figures out exactly which pixels belong to the object you clicked, not just in that frame. Across the whole video, object tracked, silhouette filled in, frame by frame. Now the interesting part, a vision language model looks at your video and asks itself a question. If we delete this object, what else in the scene gets affected? It outputs a list. The blocks behind it, the hand it was touching, the shadow on the floor. A second tool, SAM3, then masks each of those affected objects. After that, the vision language model predicts where those affected things will end up after the removal by labeling cells on a coarse grid for each frame. All of that gets combined into a single image alongside the original video. 4 colors. Black means erase this. Light gray means rewrite this. Dark gray is the overlap zone, where the model has to decide, and white means don't touch anything. Why 2 shades of gray? Earlier work used just 1, and it ran into 2 problems. When the affected region was huge and mostly empty, the model couldn't tell which pixels actually changed. Void fixes that by only marking grid cells where something visibly happens. And when the object you're removing physically overlaps the thing it affects, like a kid holding a ball, that region has to be erased and rewritten at the same time. Dark gray is the label for both at once. This 4-color map is the contract. It tells the model where to erase, where to rewrite, and where to keep things untouched. The original video pixels are still completely intact. Nothing has been removed yet. And one detail worth knowing. During training, this 4-color map wasn't built by a vision language model. The simulator built every scene from scratch, so it already knew what was the object and what was affected. Perfect labels, generated for free on every training pair. The vision language model only steps in at deployment when there's no simulator around to ask. Then comes the part where pixels actually change. A video diffusion model takes both inputs, the original video and the 4-color map, and generates a new version of the video as if the object had never been there. The paper calls this the counterfactual. We'll use that word from here on. Diffusion sounds complicated. It isn't. The model starts from random TV static, then refines that static into a video, one denoising step at a time, dozens of steps in total. The 4-color map is the steering wheel. Erase under black, rewrite under light gray, preserve under white, and crucially, it generates every frame at once in one shot. Not one frame, then the next, then the next. The whole clip is denoised together with attention crossing time so that objects move smoothly and don't flicker. The output is usually good, but sometimes things go strange. A guitar bends as it falls. A ball deflates while it rolls. Real physics never does this, but a model that has to invent motion from scratch sometimes lets that motion bleed into the shape of the object. The fix is borrowed from another paper called Go with the Flow. Instead of starting from random static, run a second pass that starts from static which already moves, by warping the noise along the motion the first pass produced. Now the noise itself flows like a river. The model only has to paint the object. The motion is already there. Shape stays solid. And this second pass actually uses a different model. Same architecture and same training recipe as the first one, but with motion baked into the noise instead of random static. 2 specialized models, one for each job. The second pass is slow, so it only runs when needed. The same vision language model from earlier, the one that built the 4-color map, gets called in one more time. If removing the object causes new motion, like something falling or rolling, it triggers the second pass. If not, the first pass is the final output. And one subtle thing, the vision language model isn't checking whether the object will deform. It's checking whether there will be new motion. That's not a coincidence. New motion is the thing that forces the model to invent shape, which is what causes the deformation in the first place, so motion is the right signal to watch for. Step back for a second and look at what's actually happening. Void has no explicit physics inside it. No gravity equations, no collision solver, no Newton. It is pattern matching. In a learned latent space. What physics tends to look like. The simulator had the real physics. Void just learned what the simulator's outputs look like, then mimics that, on videos the simulator could never run on. Does the imitation actually hold up? Netflix ran a head-to-head study. 25 people, 75 real-world clips, every major competitor lined up. Void got picked 64.8% of the time. The closest rival, Runway, 18%. The traditional in-painters scored basically 0. Pattern matching, trained on cartoon blocks, beat every dedicated tool on real footage. You can see the cracks if you look. Weird camera angles, unfamiliar objects, things it hasn't really seen before, those all still trip it up. A real simulator wouldn't care about any of that. But a learned imitation always breaks down once it goes outside what it knows. This is the central trait in modern AI. Real understanding versus learned imitation, that's good enough. Void is a bet that for video editing, good enough beats real. And that bet matters because Netflix didn't publish this paper for fun. Continuity errors, accidentally filmed logos, regional edits where something can't appear. The paper doesn't say whether Void itself ships in any production pipeline yet, but these are exactly the jobs a streaming studio needs done. There's another reason Netflix lets researchers publish this kind of work. Top AI talent won't join companies that don't allow it. Studios in 2026 are competing for AI engineers the same way Google and Meta do. And by putting the paper out publicly, Netflix shapes what tools the rest of the industry builds. The real moat isn't the model. It's the content library and the production pipeline that uses it. The most realistic AI video tool isn't simulating anything. It's rewriting reality, one shot at a time, and you've already been seeing it.